to the equipment while it ships and changing its status before the laboratory gets a chance to inspect it as well. So here we have a fan motor that failed, and then I've already started to take it apart, so we don't have to wait for that, but it's something important that you do. As I took this apart, I was taking lots of pictures so that the condition that it was found in could be preserved and understood. So that's something that's very important when you do this, or you have this happen on site, that you don't want to immediately just tear it apart, pull out the failed component or failed bearing, and then put a new one right back in. We want to be able to inspect and try and understand what happened, or at least be able to inspect and gather information to get to the laboratory, and they'll be able to use that along with the analysis that they do on the bearing itself and the lubricant to understand exactly what happened. So what I'm going to do here is I'm going to take my bearing. So I'm going to take the non-drive end bearing off, and then I'll hold that up. You guys can see that bearing. And then I don't want to do anything to it yet. And when I send this to the laboratory, and we'll demonstrate later what happens when the kit gets to the laboratory, but then the laboratory will be able to take the sample. So I don't have to worry about doing anything to this bearing if I'm going to be sending it into the laboratory. I'm just going to take that, and then I will put it into one of the bags provided in the kit. And that's going to go in here.
And not every bearing's that small, Richard. So there's various size bags and that sort of thing, right?
Yes, that's very, very true. So we've got some very large bags. So we'd be able to take any larger pieces of equipment here. We could put our equipment in these large bags also to send to the laboratory to preserve. We've also got some medium-sized bags. So we have bags of all different sizes, and they are of a thicker build, so these won't break just by having these, sometimes sharp metal components inside. They're heavy duty, and they're meant to be able to hold those heavy pieces of metal equipment for shipment. All right, so then next I will slide my tray over a little bit, and then I'll demonstrate getting the kit ready to ship out. So when you've got the component inside, got already the foam padding on the bottom to protect it. So we will, sorry, a little out of screen. So just open this up out of the plastic bag, and then I will open this up completely. There are instructions that are written right on the outside of the bag, and there are steps 1 through 6. So you simply would just follow the steps right down off the bag. The first step is to watch their video. We have also created a video, like I mentioned earlier, that you scan the QR code, and it'll take you to a video to be able to watch. And then to prepare that, so I've taken all my samples, I put everything inside the kit if I needed to take them, and then I put my pieces of equipment inside. So the next thing I'm going to get ready to do is to prepare them. So to do that, there's an A and a B. I'm going to push down hard on the A. It's going to push over the material. They're going to start mixing, and it'll cause the chemical reaction to happen. You're going to see me mix it. It says to pass it back and forth 20 times. I'm going to put it inside the case and close it, and then the foam will fill up, and it'll be ready and safe to ship, and we won't have to worry about anything happening to our equipment when it ships. Any questions before I start, Rich, or ready for me to start? All right. So I'm just simply going to push with my hand hard on A. You might hear a pop in the video. And then I'm going to push it back and forth. I can feel the temperature increasing. So I'm going to set that empty bag inside there I'll have my case closed so that it can fill up and expand, and it's going to hold that equipment still for shipment. And then this will take just about 10-15 seconds, and then I'll open it back up and I'll be able to show you, and the pack will be nice and full, and it'll hold your component in place for shipment back to the laboratory for the analysis for the root cause failure.
Okay, Richard, while you're doing that, I'll just make a statement why we felt this was important, because sometimes we're getting equipment that's being sent to us in the lab. There's just a lot of variation on the steps people take to isolate, to care for it, and so forth. And sometimes we find ourselves trying to separate the damage that happened while that equipment was in service and what damage was induced afterwards, right? So it could have been induced in trying to remove it from the shaft and dropping it on the way back to the desk. And a lot of times it's damage in shipment, including, we've gotten greased bearings all packed full of packing peanuts, and then you're trying to get around them and all sorts of things. So this becomes a way of securing and stabilizing this for shipment so that we don't have damage that takes place during the shipping process.
So here I'll pull it out. You can kind of see it got much thicker. It filled the entire case, and then side to side as well. So it's, I can see the indentation on the bottom from where the bearing was being held in place. And on top, I can actually see the kind of bumpy pattern from the top of the foam case. So this does a really good job very quickly of securing that component right in place. And then now all I need to do is go make my shipping label, put that on right on the case, and then I'm able to ship this case right to the laboratory for analysis. And then the really convenient thing is that once the lab gets it, they can replenish the case of whatever consumables I used, bags and sampling kit materials. And then that would be able to be sent back to me, and I will have that on site in case I'm prepared in case I have a failure. It's not what we want, but I'm ready to take care of it if it does happen.
Okay, great. So now, Richard, you're going to kind of drop off here, and we're going to go into a equipment is out there being shipped around. And so I'll take this moment to kind of go to an overview that we've put together for today. So I'll bring that document up. And so is that going to be shared to the screen, Marissa? Does that look good? Okay, I'm going to think it is. So I'm going to talk about this a little bit. So what's a root cause failure analysis? Well, we're going to investigate the failure of some component of equipment. And why is it important? Well, it's because we want to break that cycle of failure. And it may not be just one particular piece of component that's failed, or it may be that this is a situation that has applicability to other pieces of equipment, other systems, other facilities, either other places around our company. So we can break that cycle of failure if we understand what caused it. And a lot of this is around evidence gathering. It is much like a crime scene, and getting prepared for this. I talked about it's almost like CSI for capital equipment, for manufacturing equipment. But that's because we need to isolate it. We need to carefully gather that evidence. We need to thoroughly examine it and then look at all the inputs, what happened historically, what's happening in that system, how is the equipment being operated, and so forth. Use that to determine the root cause of the failure. In some cases, more than one root cause. And so with this, the challenge is in creating a timeline, right? We can say, well, this cage cracked, and point to that as a significant event. But maybe the cage cracked as the third or fourth thing in the progression of a failure, and it really wasn't at the root. It isn't what started this process. There could have been 2 or 3 other things that happened, and eventually the forces became so great that the cage cracked. So as we gather the evidence and as we observe what we can see in the materials that are presented, and that's not only just the bearing, if it's a bearing and its components, it could also be the lubricant. It could be debris that was found at the site of the failure and gathered up. It could be indentations on a belt drive. It could be electrical wiring or the insulation of that wiring. So it could be a number of different things, but all that evidence comes together, allows us to put together a progression of events that creates that timeline. And that's really key. And that allows us to create some recommendations for the future. What do we do differently? You always have to change, something about what you did in the past if you don't want the same thing to happen again. And a true root cause failure analysis will help with that. And we always strive to do that, which is to give those recommendations about what do we do next? What do we change? What additional steps do we take? And so on. So when the component fails, you look at the routine inspections of equipment. Is there any operator or maintenance inspections that have been documented? Is there process data collection about pressures and temperatures, loads? Has loads gone up or down? What's the equipment status been? Is there any lubrication activities that have been documented? Has there level checks going on? How often is grease being added? When was the last oil change? Is there any lubricant samples over history, and is that data available? So all this is trying to be gathered into this process. Is there logbook data entries? What procedures are out there, and so on? And so that, and we talked about this information preservation step. It is like CSI for machinery. So if you watch any of these shows, my family, we do watch some of these, like CSI or NCIS or some of these different procedural shows where they get to the scene of the crime. It's cordoned off with police tape. They're gathering information. They're interviewing witnesses. It's very similar to what needs to happen if we want to get to the root cause here. And so, some trained individuals should have direction authority. And a lot of times we can enhance this process with the engagement of a laboratory like ours and some of the things that we're going to be showing you here. But if you're in this process, make sure you document things, really gather that up. Preserve small or manageable parts. Sounds easy, but for years I've been, like to say, I've been dumpster diving, trying to find old components that were thrown away almost immediately after the maintenance activity, because all the focus is on getting the equipment back up and running. So preserve those parts and be careful how you handle them. I mean, there's a temptation when two parts break to try to mate them together. Like, can these bang, can I make this puzzle fit? And if you do, we might lose some metallurgical data that's there on that surface by disturbing that. And so some of the things you can't get out of the laboratory is the dimensional data, the as-found data, the alignment or misalignment, anything that was observed during that inspection, any repairs that were made. And then if there's any parts that are too big to save or ship or send on for close inspection and further analysis, take photographs. And take photographs of the conditions that must be disturbed in order to perform the repair, because we're not going to put things on hold. I mean, in the crime scene shows, they might close off a busy highway, for a period of time, and it's very disruptive. And in a manufacturing environment, a production facility, and so forth, we've got to get back into production. So we want to maybe take some photographs, gather some pictures, and we've got this great tool now with the smartphones. And that's why we built the smartphone capability into this kit, where you're scanning the QR code, you're entering the pictures that you're taking, you're answering those questions about the history and the operating conditions and all these other things to put them in one place for the analysis. And so here is that metallurgical analysis I was talking about. Don't pick those parts together. Don't mate them up. Just secure them and protect them from further damage. It might not seem logical, but do not clean parts. Don't put them in the parts washer. A lot of times I'm saying, hey, let's get a look at the bearing. Well, it's already been in a parts washer. It's already been all wiped off. All the oil's been drained off and put into a collection container. No, if you've got oil, grease, other fluids, debris, drain that into a clean sample container, or seal it in the part. And that's why Richard showed those sample collection bottles and grease collection bottles to do this. So you've got something. That's why this is meant to be a kit that you take out into the field and you hand to the individual who's going to be responsible on site where the repairs are going to happen, or just the initial investigation of the failure. You need the tools like this to be able to preserve them properly, and then choose your shipping methods carefully if it needs to be shipped. And then you can throw in some personnel interviews, just like the crimes, interviewing the witnesses kind of thing. And there's just some advice here about, being careful about that, those personnel interviews, to try to get as much information as we can, trying not to assign blame. That's one of the biggest challenges in root cause failure analysis. If you're working in a culture of assigning blame, who's responsible for this? Who caused this machine to fail? People have a tendency to be less forthcoming, less sharing of information, and it might be somewhat satisfying to say, Jack's the guy that did it, and we're just going to make sure Jack doesn't touch this machine again. That's not going to help us understand what truly factored into this failure. So it's important to have that kind of culture. But then we want to create a corrective action plan. So you'll see in our reports that's where we're driving for at the end. It's like, it's great to find the smoking gun, but then you got to say, and now what? What do we do next? What do we do differently? What are we going to change in the way that we've been doing from a procurement standpoint? Sometimes it's procurement. Sometimes we're getting the wrong parts, or we're getting parts in and then we're putting something different on top of them, or it's just its shelf life has exceeded. Whatever it happens to be, it could be in procurement, it could be in the design of the machine. This could be a motor that sits on a bad base, and we'll get new motor after new motor, and every one of them will be failing if it's sitting on this base that's resonant or has a soft foot condition or whatever. So we want to identify similar component failures and see modes and see what else we can kind of head off, even if we don't have failures, and say, there could be something coming in the future. Create some short-term and long-term plans, right? Get our units back up and running, but then in the long term, how are we going to extend the life? How are we going to make things last longer and avoid some of these failure modes? And then additionally, here's the steps, right? Once the component fails, what do you do? Well, make sure the scene is safe, right? Get to a safe condition. Then grab your MRG Labs or root cause failure analysis kit, because it's going to have everything in there that you need to get the data, to collect the information, to secure the crime scene, and to get what you need. And then take your smartphone, scan the kit QR code, and then provide the inputs that are needed. And it's going to walk you step by step through these questions of identifying the unique identifier, the equipment ID for that, and then going through and saying, well, what size is it? What speeds are involved? All these different things. What's the operating history? What symptoms were seen? Right? What's the failure? What constitutes a failure? Did it trip at the breaker, or did it catch fire? There's a lot of different things that people might define as failure. So saying what those things were, what was observed at the time of failure or immediately prior to, is important. What were the system parameters? What conditions were observed? Get all that into the repository, the website gathering tool that's associated with scanning that QR code. And then collect all that evidence together, follow the instructions provided in the kit, and keep them isolated, right? Get them into these closable bags. And don't let outside contaminants get in there. Get the fluids into the containers that they need to be in for testing. And then it all gets back to the laboratory for analysis. So you saw Richard sharing this kit and what's in it. It's got 4 heavy-duty, medium-sized bags, 2 heavy-duty, large bags. It's got these 3 packs, so we can kind of pack them around. This one was an easy one today because it's a small bearing, just goes right on top. But you have things of different shapes and so forth, so you can get these packs together and really put multiple components in there, secure them, keep them from banging into each other, and get them back for analysis in good condition. There's the Grease Thief is our sampling tool. You've got the chance to take grease or other semi-fluid samples and secure that. It could be caulk material. It could be something else that's grease-like. Gather those samples up. Some oil sampling bottles as well. And then the documents are there for how you prepare it, how you sample it, how you use that foam pack. And then once you once you get this closed, it's waterproof, it's durable, it's going to protect that evidence until we've got more time to look at it. Keep safety first. Keep safety first at the failure site. Sometimes failure sites can be pretty significant, damaging, violent, a lot of forces involved, compressed air perhaps, parts are under tension or compression or whatever that can release that energy. Make sure that we've got the failure site in a safe condition. And remember, when things fail, especially metallic parts, they often become sharp. So you might be handling sharp edges. So have the right gloves and the safety glasses that are going to keep you safe as you go through this. Even like lubricants or other fluids that were safe going in could have reacted, and now they're unsafe. So we've got to look at that. And as we said, preserve all that information. Again, don't clean the parts off. Whatever's on them, isolate it, put it in the bag, seal it up, and let the lab analyze it, because it may really tell a lot about what happened here. So you want to save that. Okay. And then there's some steps here that you saw Richard go through, in addition to marking the bags. Okay, make sure that you clearly label what you got there, and part of that's going to be done with the smartphone as you scan the barcodes and apply labels to things, and then insert those components. Let those bags kind of expand and form over it, like Richard showed us. So I want to circle back now to. Richard should be ready to do a live demo. We're going to show you what happens here next when we get the kit back in the laboratory, and then give you some insight here on what happens to it there. So, Richard, if you're ready, let's go to the lab, open up that kit, and see what we can get. Now, you're pretty out of focus right now, Richard. I don't know if you can make an adjustment there, but yeah, it's a pretty blurry image right now.
Move the light a little bit. Maybe I got it the wrong spot. Can you see it okay now? Is it blurry?
No, it's quite out of focus.
All right. Let me try last time. As weird as it sounds, that the mat had caused us an issue before.
Yeah, it didn't seem to change anything. You have a label there in the foreground, and it's completely illegible.
Yeah.
And when you started, it seemed okay, but something happened along the way. It refocused on, there. You can see that.
I'm trying to get it to refocus. That's not doing it, dang it.
Do we have perhaps another camera we can, or maybe just reset? You did reset the camera then?
I tried to. Try it again. See if I can give it a second to reset.
Is that a USB? Maybe you pull the USB so it powers down altogether and starts again.
Any better? No. Nope. All right, I can do that.
You could also try turning off the light. It might be off the for another.
Trying both of those suggestions. I think I might have to rejoin real quick.
So while Richard is doing that, I'm going to pivot back to sharing a document that I have here, which is one of our root cause failure analysis reports. So this will give you an idea of the, what's the output of all of this. Whoops, that's not it at all.
All right, much better looking now. So thank you for those suggestions, Marissa and Rich. It helped, and I think everybody can now see what we're doing.
Nope, hold on. I'm doing a shared screen.
Sorry.
Okay, go ahead.
Okay, so we've received our kit back at the laboratory. So once we get that back, we will open it up. And then here, take out our packing. And then here we've got the non-drive end labeled, if you can read that. It's a little hard on the shiny plastic bag, but NDE, so we know that's the non-drive end. And then I already have over here on the tray the drive end bearing out of the bag. And then we have our little tool here. So these are double shielded bearings. So there's a shield on both sides. So just going to use a little bit of isopropanol, make sure that the tool that I'm going to use doesn't have anything on it before I start to remove the seal of the bearing. And what I'm getting ready to do is open up the bearing, and then I'm going to take a sample that the laboratory is then going to use for analysis. So simply going to work my tool under the edge. I'm going to be real careful not to put too much pressure or force. I don't want to do any more damage than what already might have been done. And I'm slowly just going to lift up. So this is a nice little kind of plastic shield, so it's going to come off nice and easy. So now you can see on here, kind of get closer to the camera with the light, you've got the bearing and you've got some grease inside here, and then I've got the shield off. So
Richard, I'm gonna point out that I did a posting on LinkedIn earlier this month on these bearings, and these came from my farm. These came out of a piece of hay working equipment. I'm guessing that they're at least 30 years old because the side of these bearings said it USSR on it, so that's the Soviet Union. This apparently was an East German made piece of equipment, and so I can't consider this bearing a failure or a premature failure in any way. And with its age, we may not have as much grease as you would expect, but it looks like we do have some grease available, right?
Yep. So I'm going to open up the kit, and then open up my syringe, and I will hold the plunger in my hand just so that doesn't have a chance to get on anything. And then I'm going to use the small side of the spatula, and I will begin removing the grease.
Now, normally we're targeting a full grease thief, right? Which is about a gram of grease. With a bearing of this size, its age and so forth, we might have a hard time getting anything close to that, right?
Yeah, it may be challenging. My thought is that if I open both sides, and it has quite a bit on this side, so I'm hoping if both sides of that full, we'll actually get a fair amount from a bearing this size. But yes, sometimes the smaller bearings do not have a lot of lubricant inside of them just due to the size of the bearing, and that can be a challenge.
So what do you do in that case? Should folks still try to get the grease they can, or if they can't get that much, it's not worth it? What should folks be thinking about?
Yeah, in a situation like that where if you might be afraid to lose the sample, that might be a really good time where you leave the sampling kit in the you don't try and take the sample yourself, and I would just take that bearing if you think it's going to be really challenging and send that to the laboratory, and then allow us to be taking the samples. And we have a few techniques in the laboratory and instruments that would allow us to do some testing. So depending on the size, we might be able to take that bearing and do some non-destructive testing and put that into some of our instruments and get some results without having to do anything to the grease. Then when we go to remove it, we've already done a few tests, and that lowers the amount of sample that we need to complete our full analysis. So the lab can kind of be a benefit there, where if you don't touch anything, we can run some tests before it's too late and it's already been taken out of the bearing.
Right. So in this case, it's like this is the whole bearing's been sent to the lab. So we've got the opportunity to get everything we can from it, or if there's only small amounts, we have some other techniques to test it anyway.
Yes. So, for example, one of those techniques we've done one of our Grease Thief Thursdays on was PAS FTIR, and we've been sent bearings so small that they can fit inside the sample cup, and we can put the whole bearing inside and then scan the grease inside the bearing, so we're able to get an answer for the customer without having to try and remove any of the grease. So it kind of takes the level of effort down, but it increases the value of the data that we're able to provide. So that's a very useful test for us in the laboratory.
Talk about the seal a little bit that you remove, because sometimes in the removal of the seal we impart some damage, but sometimes we can see damage to the seal that's happening in the field still, right?
Yeah, so I'm cleaning that off right now. Sorry, my hand drifted back. So I just got a little grease out of there, and then I can. So the seal, if I can get it under the light, relatively in good shape. I don't see any kind of damages on the front or the back. There's not any kind of like scarring or signs of kind of contact between surfaces. So I can hold that up there. It's a little hard to see just because it's dark. On the back side, has a little bit of grease on it. We have seen, and I'll show you an example here when we talk about the next steps for the analysis, but we have seen some shields with some considerable damage from some of the failures that we have gotten in the laboratory. So gathered my sample from that side, and then as we've shown before, my next thing is going to be packing up my sample, and then this sample is going to be given to the laboratory, and then the laboratory is going to perform as much analysis on that as possible. So some of the important things that we've talked about before, and as Rich mentioned, if we can get a full grease thief, it's really nice because we're going to be able to do our dye extrusion, and then we're also going to be able to use the rheometer. We've talked about both of those methods before on some videos, and those help us understand the consistency and some of the rheological properties of the grease and kind of how has that changed while it's been in service. And those are very helpful for understanding the failure. We're also able to take that grease and, as we mentioned, do FTIR. And that's going to help us look and understand contaminants and some other things. And then we can do elemental analysis to look at our elemental levels, understand the amount of wear that we might have in the sample, as well as confirming contamination that we might observe in the FTIR spectrum. And then another really helpful one is our antioxidant properties. So being able to run the ruler test on the grease and understand, are there antioxidants additives still in there, or are they depleted, and maybe is that part of the cause of the failure?
So we've separated out the grease in the lab. We've observed the condition of the seal, and then a lot of times, depending on the bearing geometry, for instance, we might be cutting that open so we can see some of those other surfaces.
Yep. That's perfect leeway into my next example I have here. So in the corner, then I have an example of what would happen after the bearing has been sampled. So here I have an example of a bearing that's very similar in size. It actually belongs to that fan motor that failed. So we get these cut. I'll try and raise my light up so that I can get it closer to the camera. You guys can see this. There are lines. So we have a machinist who is cutting for these. It's really hard to see because of the metal surface, but there's a red line right here that indicates right where the cuts are going to be made. And then that lets us know that if there's any other kind of damage on the inside, that it did not come from the cut that we imparted on the bearing to get it opened, and it's coming from the damage that the bearing sustained. And then cutting it allows us to be able to open it. We're able to inspect the inner raceway, and we're able to look for some pitting. So this inner raceway here Same thing, we'd be able to turn that around, look over that, and it allows us to kind of inspect and to take pictures to include in the report for the customer. And then, as Rich mentioned, some seals. So the one side from this bearing is very broken. You can see it's kind of chipped along the edges here, and then there's a chunk missing right in that seal. And this was as found condition. This was put in the bag and sent to us.
So Richard, that's actually a shield in this case, right? Because that's all metal.
Yes, this is from a bearing that was shielded with 2 metal shields. Yes.
Okay. All right. So shields and not seals in this case. Okay.
Yes. Sorry. And then the other one is even on the other side is even on worse condition. And here we can see that the shield is actually being bent in. And what we found on this bearing was that, as we talked about, it's a double shielded bearing, but the piece of equipment also had a Zerg fitting on it and then no relief port. So grease was being added onto at the end through the Zerg fitting. It had no purge path to go out, and so the grease pressure was just building up, and eventually the shield became the weakest point, and the grease started to push the shield into the cage material of the bearing, and that ended up causing one of the failures in this piece of equipment.
Yeah, that interesting. In that case, there was a relief hole on that motor housing, but it was covered up with a plastic plug that was put on for painting purposes. So the manufacturer had put plugs over the holes and then painted it, and then typically would remove those plugs, put Zerk fittings in and other things, but they left that plastic plug in place, and it blocked up that purge path on that motor housing.
Yep. And one thing I forgot, and I might be able to kind of point it at the camera and help you guys see a little bit, is we use this magnifying glass to be able to look at the equipment. And this allows us to really inspect it. Some of these are just a little bit too big to put under our slide microscope, but it allows us to get in there and really inspect and understand what's going on. This is really helpful. It's got, as you can see underneath, it's got the bright light. It's going to allow us to really understand what's going on there. Next thing I was going to show you was the cage. So same thing, when the bearing gets cut, we also have the cage. If we don't need to, this one actually had some damage and the cage was broken. On the end there, you can see the cage, or the one section got ripped open and it broke the connection on the other side. And again, this is corresponds with that one where the shield was being pushed in from the grease. So there's just an interesting thing about that too, is on the one side, it's nice and shiny, brand new, doesn't have any damage. You flip it over on the other side, and there's lots of fatigue and wear on the surface. So you can see the side that the shield was being pushed against on the cage.
Right. And as I was saying earlier, the challenge here is there's multiple things going on, and it's like, what happened first? What started this whole issue? And I think, like you said, Richard, on this particular one, there was a whole independent second root cause failure taking place at the same time as this collapsed shield into the bearing.
Yes, and I can mention that as well. So here are so that's a perfect example of why we work with one of these metal trays. So I didn't try that. That just kind of happened to work out well. But when we're working with the ball bearings, they tend to want to roll away. So it's nice if you have a surface with a lip that you can't lose anything, and this project stays. If I'm not working on this, I actually would take and put this over on a shelf that we have that protects it, so it's not just always sitting out until we're done the project. But with the ball bearings, we would also, same as the raceways, we would inspect those. Interesting thing about this one is that some of the rollers looked in relatively good condition, And so, for example, this one, I don't know if you can kind of see, it still's got a shine to it. It still had its luster. And then some of them were a little bit more dull, and it's hard to tell because of the light just shining on the metal. But with your eye, when you observe them, it was easy to note that the balls also had a flat spot, and that flat spot would have been caused when the shield put enough pressure on the cage, and then that would have locked the rollers in position, and they weren't able to freely rotate as intended, and then that started to generate a lot of surface fatigue inside the bearing. And then the other issue that we had with this one was that the housing itself was not properly tensioned. So our rods to hold our housing together actually were loose and vibrating, and that allowed the rotor to rock inside the stator, and it was making contact till eventually it was moving too much. And so there was two, like Rich mentioned, or we mentioned, there was two simultaneous and independent issues happening with the fan motor. So if it wasn't one, the other was going to take it down.
Yeah, that's great, Richard. Hey, thanks a lot for showing us both ends of the process here, both the collecting and taking the bearing off of the motor, getting the parts together, getting it into the MRG root cause failure analysis kit to secure all that and get it to the lab, and then showing us what happens to the lab in a typical bearing that shows up. But you're not done with that, right? We're gonna finish the analysis on those bearings that you just kind of shared with us on these two new bearings. Compare them. This is an interesting one too, because the process for replacing these bearings was to provide information on them, because they're very old bearings, to a supply shop, and they gave us replacements. But I have a feeling we're going to find this low speed bearing application that the grease really needs to be different. So that could be a mistake that folks could make. Hey, what's the size of the bearing? Get a replacement for that bearing. But when it's a sealed bearing, you're also factoring in the grease, and is that grease the correct grease for this particular application? And speed has a lot to do with that. So, Richard, thank you. I'm going to just finish it up here by sharing a document, which is the what happens now. What is the root cause report that you get out of this whole process that we shared today? So I want to bring that up on screen here and switch this to kind of the full screen mode. So Marissa, help me. Can folks see that tuning in? Can they see our root cause investigation report?
Yes, we can see that. Yes.
Okay. And then if I just page down, then it switches the pages in the view?
Correct.
Great. So this is just a kind of a generic one from a blower, two different size bearings here, a drive-in and a non-drive-in coming out of that motor. And this shows you what you'll see. Will kind of give the purpose of the analysis, what happened in this case and why we're doing the root cause analysis, the methods that we used, including some of the laboratory experimental methods or detection methods that we use to evaluate the grease in this instance, or the residue, or what have you. Then we share the results and the analysis, including some of the spectral analysis. We've got here the FTIR comparing the reference lubricant to the lubricant sample that was submitted. Then we also have here the ruler results, which shows the antioxidants that are in there. We've got images from analytical ferrography from the debris that was isolated. Sometimes that debris is still in the bearing or the housing or on the other component. Sometimes it's in the lubricant and it gets isolated. Other contaminants that are there, that the contaminants that would have led to the cutting wear particles that we saw. And then some interesting things like showing and detailing with kind of close-ups and arrows and things like that, wear patterns. And you can see this kind of X wear pattern on these balls that shows that this was heavily axially loaded and constrained, and then it was released and it started that wear pattern again. So that's very insightful into what was happening in this particular bearing. And then not only on the bearing raceway surfaces, but on the mounting surfaces as well, looking for indications that there's perhaps some issues here, because when the bearing fails, sometimes folks just say, get me another one of those same bearings and I'll put it right back in the housing. And if the housing itself has a fit issue, you could be right back in the same situation again. Other sometimes it's not the root cause, but there's other things going on. In other words, we may help someone eliminate that root cause, but there is a secondary cause that would be another source of failure right behind it. In this case, there was a lot of particulate in the grease, and it has this particle denting and these scratches on the surface through fatigue and abrasive wear. So, it's not good enough to find one smoking gun. If there's multiple contributors, we want the customer to know them all and eliminate them all and get maximum life, maximum performance, return on assets, if you will, and reduce the incidence of failure altogether. And then just sharing all these different data points. And you'll see, of course, there's two bearings here. So we go through the whole process again, two different conditions between them in this case, had some false Brinelling. But to finish it up, we've got this summary here at the end of the bottom of this page of causal factors and the root causes, the root cause being that one thing that kind of kicked this all off, but these causal factors and secondary issues that need to be addressed as well if our goal truly is to maximize the life and minimize the incidence and the risk of failure in the future. And then, of course, the corrective actions and recommendations that we make based on these observations, based off of the inputs and so forth. So this is where it becomes a multiplying effect, where it's not just, hey, this one machine failed and now we understand it, but how do we address this machine in the future? How do we address systemic issues that are being observed in this failure that could be applying things across the board? And that's why lubrication is so important. Some folks say, just clean up the bearing for me, let me look at the wear patterns. But a lot of information can reside in the lubricant itself. And so if we don't have that, if in the lubricant, those can be systemic. They can be about using the wrong grease for an application. They can be about mixing of greases that are incompatible that led to this. They could be about the frequency. The grease was just allowed to age too much in the equipment, or it could be from contaminants that have gotten in, or we might find wear patterns that are specific to a certain causal factor creating that kind of wear. So there's so much locked up in the grease or lubricant or debris that it's a shame to not include that, and we miss out on a lot of really targeting what needs to be done. So I want to thank everybody that joined us here today. And we've been live streaming this on YouTube, so there's a recording of this as well. But it's really exciting for us to introduce this new kit and give people the tools that they need. Look, I started my career in the plant, in the maintenance department. I went jumping in dumpsters to find old parts and so forth, tracking people down. And if I over those years, if I had this kit available, I knew I could have just parked it there when we had an issue and said, hey guys, when you're getting this unit back up and running, like I know you can do, gather this information, or being right there to gather it, because now it's got a place to go. We just had a customer the other day that said, hey, we have a bearing failure and it's headed your way. And then they had to come back and say, well, somebody said they left it on my desk. They must have put it on somebody else's desk. That person didn't know who it was, what it was, and they threw it away. You get it into this orange container. You get it into this bright orange shipping container with the shipping information on it and all, and the identifying information. We're going to capture it. We're going to get it back to the lab. You're going to get the benefit of this root cause analysis. And just to kind of maybe a little bit of excitement about what else is out there, well, the next kit we're coming out with is a filter failure analysis kit. And we've been doing filter failure analysis for a long time as well. Some really critical components, finding out some fascinating things. We did some filter analysis the other day, and based off of the deflection of the filter, we were able to determine that this was not a overpressurization, but actually an operating condition of that asset that was forcing it into bypass. And just, there's so much we can learn from filter analysis, but it's hard. They're a mess when you take them apart. So we're building in a kit that allows you to kind of capture that, secure it, make it so it's not messy, make it so that the oil both upstream and downstream of the filter has been captured, and then we can get it back to the lab, pull that apart, backwash the filter, look at the components under the microscope, analyze some of the debris that's in there, and gain all the information we can. So this kit that we showed you today, the root cause failure analysis kit, is available now. It's on our website. Encourage you to get one or two of them, get them stocked at your facility. So when that failure comes up, you grab them and you go. And soon we'll be able to put those filter gathering kits together for you as well. So thank you. This is our new frequency, which is once a month. So Marissa, what do we have for the next scheduled Grease Thief Thursday? When is that going to happen, and what's our topic going to be?
Hi, Rich. Great question. So our next Grease Thief Thursday is scheduled for July 15th. And our event for that is going to be robot grease analysis. So that's going to be July 15th, and the topic is going to be robot grease sampling and analysis. And you can register for that on our website. I can put the link right here in the comment section where you can register for that. It's free, and invite everyone.
Yeah, that's going to be a great one for folks who are in or working with people in the automotive industry, which is a very heavy user of these robots, especially in the US, where we're using a lot of the Japanese robots, which have grease lubricated joints. We've had some great experience with that. We have a specific Grease Thief kit for sampling those robot joints, typically joint 1 through 6. And it'll be exciting to share that, some of the case studies from that, and what the tools are and how we go use them. So hopefully we see you back there again next month. And thanks for your time today.